Hello, in this short video, I'm going to give you a demonstration of ZAFL, a binary fuzzer. A critical feature of ZAFL is that it works directly on binaries. No source code is required. ZAFL was developed as part of the AWARE project, a collaboration between AIS and ZAFL software. ZAFL is based on the American Fuzzy Lob Fuzzer, or AFL, from Google. AFL is one of the best known and most effective fuzzer in the world. To prepare a target program for fuzzing, the typical AFL workflow is to use a modified version of GCC or Clang to compile a target program so that instrumentation can be added to guide the fuzzing process. For real-world software, the difficulty of modifying the build system or even having access to the source code is often underappreciated. Instead, ZAFL operates directly on the target binary without requiring any source code. ZAFL inserts the instrumentation that AFL expects using an efficient, patented binary static rewriter called Zipper. ZAFL is 100% compatible with AFL and can leverage tools and utilities actively developed by the AFL community. We will use BC, a calculator utility program, to demonstrate ZAFL's ease of use. It only takes one simple command to take a binary and make it fuzzable. We specify the target binary, in this case user bin BC, and the name of the output binary, in this case bc.zafl. That's it. One simple command to prep a binary for fuzzing. AFL requires that fuzzing sessions start off with at least one seed file. So let's go ahead and create a seed file with the content, "Hello, how is the weather in Rome, New York?" So now let's go ahead and fuzz the program that we have just ZAFL'd. Note that the command I'm typing is a standard AFL command which comes pre-installed with Ubuntu. There are no changes needed to AFL itself to run ZAFL. And there we go. Voila! The AFL dashboard has come up and we're now fuzzing. All the stats that you see on the screen are the standard AFL stats, things like fuzzing execution speed, number of unique paths, and number of crashes found. Let's go ahead and take a look at some of the inputs that the fuzzer generates. As you can see, these inputs are definitely machine generated. If you look closely, you can see remnants of the original seed inputs that we provided earlier. That's the power of fuzzing. It will try pathological inputs that humans simply wouldn't come up with. Let's talk about ZAFL results. These were obtained by a third-party evaluation team. To the best of our knowledge, ZAFL is the fastest binary fuzzer in the AFL ecosystem. On average, ZAFL is 60% faster than AFL Dynast and 228% faster than AFL QEMU. Given the same time budget, in this case 24 hours, ZAFL generates a lot more inputs than either AFL Dynast or AFL QEMU. ZAFL also finds many more crashes given the same time budget. ZAFL scales to real-world software. A fuzzing startup provided us with a large 140 megabyte challenge binary used for machine learning. Using ZAFL, we were able to fuzz the binary, find a new heap overflow vulnerability, all before the startup was able to even build the binary. This anecdote speaks to the robustness of ZAFL and to the advantages of fuzzing binaries directly. Next, we demonstrate the use of ZAFL in support of DevOps. To motivate this use case, we note that the cost of fixing security-critical bugs grow exponentially throughout the software development lifecycle. NIST estimates that the cost of fixing a bug that has escaped to deployment can be 30 times higher than if the same bug had been caught earlier. In traditional DevOps pipelines, the automated and continuous testing of code is already a standard practice. To increase the quality of code and catch security-critical bugs early, we advocate for the additional use of fuzzing in DevOps pipelines. By working directly at the binary level, ZAFL enables fuzzing to be easily integrated into DevOps pipelines, as it does not require developers to modify their build system. Let's demonstrate using our Git repo for libeHP, which is an exception handling parsing library that we released open source. We've configured a pipeline to include a fuzzing pass. Any code committed or merged into the master branch triggers a fuzzing run. The duration of the fuzzing run can be customized. A typical configuration is to use short fuzzing runs on a per commit basis, but then run a more extensive fuzzing session overnight. Let's go ahead and make some edits to a header file and then commit the changes. The commit triggers a GitLab pipeline which builds and tests libeHP on multiple platforms. Once all the tests pass, the fuzzing stage of the pipeline starts a new fuzzing session. Inputs found in previous sessions are reused and serve as regressions. Note that fuzzing is an inherently parallel process. If desired, lots of hardware can be dedicated to fuzzing, and that would be especially useful for security-critical applications. When ZAFL finds a crash, it automatically files a bug report. Let's go ahead and look at the previous bug report. Here, the fuzzing stage of the pipeline has failed. Looking at the fuzzing logs, you can see that ZAFL has found 25 crashes. Attached to the bug report is a YAML file that contains detailed information about each crashing input, along with enough information to reproduce the issue. We provide tool support so that developers can easily reproduce crashes. Thus, bug reports produced by ZAFL are easily actionable. If you would like more information, please do not hesitate to contact us. We will be happy to answer any questions you may have.